Hello, welcome to another graduate classical mechanics video from Dr. Viv. This time we'll look at the generalized forces in the Lagrangian formulation. A very important example of this is classical electromagnetism. When I say classical, I mean there's no quantum mechanics. So we'll first write an expression for the generalized force using the Lagrange equations of the second kind. And then we'll, as an example, look at non-relativistic electromagnetic theory. We'll look at the Lagrangian, the equations of motion, a very important quantity called the Jacobi Integral, and also our old friend, the Hamiltonian. Then we'll repeat for relativistic Lagrangian and Hamiltonian. And we'll also show in the process that the Lorentz force is relativistic in origin. So let's begin by writing the Lagrange equations of the second kind. The equations of motion of the second kind, which, if you want to put a date on it, was invented by Lagrange or devised by Lagrange in 1788. And it's as follows: d by dt of del t over del qj dot minus del t over del qj equals capital Qj. J here runs from 1 through n, and the integer n is 3n minus k. So I'm thinking of n particles in 3 dimensions. N particles in 3 dimensions have 3n degrees of freedom in the position space or configuration space, which is what these QIs measure. K of these are tied up in constraints. So there are K constraint equations given by GIs. So that's the count here. So I'll write here, N is the number of particles in 3D, and K is the number of constraints. Because the Lagrange equations only go from 1 to little n, where n is 3n minus k, it means the constraints have already been incorporated. So in this sense, this is like the minimal Lagrangian, if you wish. Although we are not writing it in terms of Lagrangians, we are writing the kinetic energy term only, and this Qj is called the generalized force. All right, now that I've introduced what the generalized force is, let us look at a specific way of looking at this generalized force. So first of all, I'm going to take the coordinates x sub I to be x sub I as a function of q1 up to qn, possibly time. So I have these coordinates x sub I. So there are as many coordinates as I need here. So I go from 1 to n. So you have as many coordinates as you need. Xi dot will then be del xi by del qj dot plus del xi by del t. That's merely by the rules of partial derivatives. So the kinetic energy T can now be written. It's a sum over all the I 1/2 mi xi dot squared. I can write this kinetic energy. If I substitute for xi dot, I'm going to get 3 kinds of terms. I'm going to call them T2, T1, and T0 based on what power of Qi dot or Qj dot is there in them. So T2 will have powers like 1/2 mi. It'll have these terms quadratic. So del xi by del qj times del xi by del ql, qj dot, ql dot. Here I'm using Einstein summation, which says that repeated indices are summed over. So I is a repeated index, it's summed over. Here I wrote the repeated index. Even though it's a repeated index, I indicated the summation sign there. But in future, going forwards, I will not do that. So I is summed over, J is summed over, and L is summed over. So it's a mega summation here. This is written as 1/2 AJL QJ dot QL dot, where AJL is a so-called kinetic energy metric. We have encountered this before in the double pendulum example, where I asked you to find the kinetic energy metric in that problem. So AJL would be MI del XI by del QJ times del XI by del QL. In that example of double pendulum, we had a dot product, which is basically the numerator. It's del XI, del XI. So that's how you get a dot product. So that's your kinetic energy metric. The T1 and the T naught terms have other things. So let us look at that next. The T1 term will be purely linear in the velocities. So I'm going to get del xi by del t. So you get a linear term if you mix up one of the time derivatives with one of the space derivatives. So that's what I'll do here. Del xi by del qj times qj dot. And then finally, the t naught term will be time derivative squared. So it's 1/2 mi del xi by del t, the whole thing squared. These are the three terms you'll get when you write the kinetic energy out like that. Now, typically, these two will vanish for scleronomic systems. And that means we have time-independent constraints. So anyway, that's the kinetic energy term. Now let's look at the QJ term. What kind of QJs can we have in the simplest QJ is what we had so far. So let's look at the simplest possible generalized forces. These are generalized forces that only depend on the positions and not on the velocities. So there'll be no velocity dependence. Let's see what form this takes. Then QJ will typically be of the form negative del V by del QJ. It'll be some function of the QJs and some function of time, but we're going to assume that there is no time dependence. So we're going to write it like this. Okay, then we'll define a quantity, L, which is T minus V. Well, that you all know that's a Lagrangian. And I'm going to write the Euler-Lagrange equation of motions of the second kind using this. So I'm going to get d by dt del t over del qj dot minus del t over del qj is equal to q sub j, which is negative del v over del qj. Now you observe that this side only depends on qj. It doesn't have any qj dot in it because capital Q has no qj dot in it. So I can simply write t as t minus v or L, in other words. So this gives me d by dt del L over del qj dot minus del L over del qj equals 0. So I've brought this to this side and written t minus v common. So del by del qj dot qj of t minus v, and here del by del qj dot of t minus v. V does not depend on qj dot because it's only a function of qj, possibly time, but we're going to ignore the time. So we only have that. Even if it's a function of time, it's okay you can have this to be a function of time as well. So I'll write it as qj comma t. So that's a very special case, and that recovers for us our usual Euler-Lagrange equation. So you can see that what people think of as Euler-Lagrange is a special case of this more general case. Now we're going to take this one step. So that's the Euler-Lagrange equations. Now, what if you had a more general type of term? Now, first of all, if you did not want to incorporate a constraint, so this is Euler-Lagrange equation with constraint incorporated. Remember, I told you the little integer n is 3n minus k, so you're incorporating the constraint. What if you did not want to incorporate this constraint? Then we have to use Lagrange multipliers. So we have to write the equation as follows. There are two conventions here. The Lagrange multipliers can appear with a plus or a minus sign. So I can write this as del L by del Qj, plus or minus lambda j del Gj over del Qj. I probably should write this as different index, Qk by del Qj equals 0. So this time we have not incorporated the constraints, but have kept them independently as Lagrange multipliers. So that's the other thing we can do. So I'll write, incidentally, the plus sign is found in books like Marion. It's an intermediate level book. And the minus sign is found in books like Goldstein. And that is the graduate, classic graduate level book. Okay, I really don't care, plus or minus signs. And so the constraints, the constants go like this. If, I goes from 1 through k. Well, k goes from 1 through k, so I should have used I here. K goes from, I call this k bar. K bar goes from 1 through k, and j goes from 1 through n. So this time the constraints have not been incorporated, but have been, so this is called a Lagrange equation of the second kind, with constraints as follows. You have k constraints of the form gi equals gi as a function of q1 up to qn, comma t equals 0. So I goes from 1 through k. All right, so that is that completes the theory of generalized forces of that type. What if you had generalized forces that are a little more complicated? And that is what we need for the electromagnetic Lagrangian. So we have to first write the expression for the generalized force, which has velocity dependent this time. In this velocity independent case, you will not get the most general situation. So the second case we'll look at is Qj. In addition to having a term like that, it has a term that looks like kinetic energy. So we'll write it like this: d by dt del u over del Qj dot minus del u over del Qj. You'll notice how closely this mimics the Euler-Lagrange equation itself. So this is considered a very general way of writing the generalized force. U here as a special name, it's called the internal energy of the system. So it's sometimes called the internal energy function. So it typically has potential energy terms plus terms which involve dissipation, like energy loss and things like that. So it can be very general. So now we're going to write a general expression for this, for Qj. So you may think that Qj could have terms quadratic in velocities. For example, it could have things like this: del u over del qi dot, qj dot, del qj dot, qi double dot, things like that, plus other terms. So we're going to assume, and this is a simplifying assumption, that we don't have terms like this. The logic behind that is this. If you have terms like this, they look like the terms you would have in the kinetic energy anyway, the terms which I call the quadratic terms, things like this. It would start looking like that. So we imagine that those have been absorbed into that. So we won't write any terms involving this. So with that understanding, we can specialize this more general situation to the special case. So I'll write here a special case of U, which looks like this. It is Vi Qi dot plus V. So this is a very general form still, but it's a little bit less general than that one. So we're going to assume that our potential function, internal energy function, can be written like this, where Vi are functions of Qi and time, and V is also a function of Qi and time. So that's going to be our most valuable internal energy function going forward. And the electromagnetic Lagrangian is going to come out of that. All right, so now let's focus on this function. There are names given to Vi and V because they are so important. Vi is called the generalized vector potential. V is called the generalized scalar potential. We will see when we do electromagnetism that this corresponds exactly to what you normally know as to be the scalar potential and vector potential in electromagnetic theory. This video assumes, incidentally, you know a little bit of electromagnetic theory at the undergraduate level. So substituting back into that, let's see what we get. My Qj is d by dt of del u over del qj dot minus del u over del qj. Let's put the expression for generalized the internal energy function in this form. So I'm going to get from the first term, I'll get d by dt. When I differentiate with respect to qj dot, I only pick up contributions from that when I equals j. Otherwise, I do not. So I'm going to get d by dt Vi times delta ij. The delta ij is 0 if I is not equal to j. Minus, and this term here will, that's what I will get from that. And then when I substitute over here, this one, I'll Qi dot will be left unharmed. And this will only attack the Vi. So I get del Vi by del Qj Qi dot. And then, of course, this term will not have any time. It'll have time, but it'll be differentiated with respect to Qj. So that gives me del V over del Qj. So these are the terms we get. Now I'll apply the delta ij, Kronecker delta ij. So that gives me d by dt of v sub j. Okay, because when I is not equal to j, this vanishes. Now d by dt of vj can be written as del vj by del t plus del vj by del qi dot. So that is in turn, I'm writing that as that. So this is just d by dt, the total derivative of vj written like that. And then the other terms go along for the right. So I get del vi by del qj, qi dot minus del v over del qj. You'll notice there's a very curious looking term. So let's assemble these. So I'm going to get, I'll bring this term here up front, negative del v over del qj, and then the time dependent part, del vj over del t. And then we're going to get a term that has the following structure, del vj by del qi minus del vi by del qj multiplied by qi dot, because qi dot is common to both terms. So we have reduced the generalized force to that. This is the scalar potential gradient. Because remember, I called capital V the generalized scalar potential. So this is the negative gradient, in fact, of the scalar potential. Well, that's going to produce the usual force terms. Well, this is the vector potential that could depend on time. So this is time dependence. It just teases out the time dependence. And this term, because of the appearance that looks like a curl, this is called a gyroscopic term. And this is the antisymmetric generalized vector potentials curl. So we have all these magnificent terms in the generalized force now. I think this is as far as we need to go to, this is the theory we need for our ultimate aim, which is the, so we have finished the first part, write an expression for the generalized force, which will be used to write the non-relativistic E&M Lagrangian, the equations of motion, the Jacobi integral, and Hamiltonian. I'll talk about the Jacobi integral as well. All right, now let's move on to the electromagnetic Lagrangian. Well, E&M proceeds by choosing the internal energy function U. The U function chosen is E times phi minus E times V dot A, where E is the charge of the electron. Or the proton, it doesn't matter, charge of any charged particle that is moving, okay? So the vector potential, because of this form, whatever appears, the UIs, remember, has got this general form. So whatever appears with a velocity must be V sub I, and whatever appears elsewhere is capital V. So we can identify what our V sub I and V are. So V sub I is going to be E times AI, and V is going to be E times phi. So that's really great. Now all we have to do is substitute it into the into this term here to find the generalized force. So that's our next aim. By the way, if you were wondering what this phi and A are, for those who have taken electrodynamics, it'll be no mystery. Others will just have to accept this. The electric field is given by the negative gradient of phi minus del A by del T. And the magnetic field B is given by the curl of the vector potential A. So this is the usual E&M fields, electric and magnetic fields. The other thing, to be consistent with the traditional usage in electrodynamics, we're going to use Xi instead of QJs or QI. All right, let us now proceed to write the electromagnetic Lagrangian. So let me write it in summation convention here, E phi minus E times AI VI. So now it's very clear where your various terms are. That's your scalar potential, and this is your vector potential with a minus sign, and that's your QI dot. All right. So now let's substitute it into this expression. Remember the minus sign is there for VI because the U function was written without a minus sign. It's a plus. So that means the minus sign must be absorbed into the definition of V sub I. Keep that in mind. So now let's form the generalized force. So Qj is that. So that's going to be negative. I'll copy it. Del V over, except I'll write Xj instead of Qj, plus del Vj over del T, plus del Vj over del Xi, minus del Vi over del Xj, times the velocity Vi. Qi dot will be Xi dot, but Xi dot is Vi. All right, so that's our generalized force. Now let's substitute the all these things. So I'm going to get negative E times the jth component of the gradient, because when I take the derivative with respect to Xj, I get the jth component of the gradient. And then because of that minus sign being there, this next term gives me minus E times del Aj by del T. And then the last term is plus E times del J Ai minus del I Aj times V sub I. So I get this very pretty looking thing. I have to somehow interpret that. So that's my next job. By the way, when I say del I, I mean del by del Xi. It's a convenient notation for partial derivative with respect to the X coordinates. So now we'll try to interpret this term. That's my next goal, how to interpret that term. So here we have to recall some things we learned earlier about a general way of writing cross products using the magic circle. Remember, the magic circle is the antisymmetric symbol in 3 letters. So let us, meanwhile, try to find the meaning behind the following term. So this is a off-the-cuff calculation where we're just trying to see what this term would look like. What if I had epsilon ijk Vi times the kth component of the curl? Because I know that the magnetic field is sitting there. So I want to make it look like this. So let's see what that would be. Now, using the property of the cross product, the kth component of the cross product is just going to be epsilon KLM del L AM. Now I can bring the two epsilons together using the magic circle as I do so to bring the index K in the front. So IJK is the same as JKI is the same as KIJ. So that's what I'll do. Epsilon KIJ, epsilon KLM, and then I have VI del L AM. The advantage of doing this is now we can use the double epsilon identity. The summation over K means that you have only ij, L, and M surviving in the double epsilon identity. So that's delta IL, delta JM, minus delta IM, delta JL. You might want to review this aspect in one of my early videos on cross products and the Levi-Civita tensors. I believe it's the first or second video. Times VI del L AM. And now we applied the delta IL. Delta IL only survives when I is equal to L, and delta JM only survives when J equals M. So applying that, I get VI del I. So here I put L equals I. And for AM, I put AJ. The next term, IM, so I have to make M equal to I. And then JL, so I have to make L equals J. Remember, I can't mess with the index. Well, I is summed over, so I have to just make sure I is summed over now also. So I get VI del J AI. And that is the same as VI common del I AJ minus del J AI. So that term there was precisely equal to epsilon ijk VI del cross AK. So now we have completed the sidebar calculation. So now we can write our generalized force. You're in for a great surprise now, because the generalized force will turn out to be something very familiar. Minus E times del phi j. And this part remains the same, minus E del AJ by del T. And now this is going to be written, because I have IJ minus JI, and here I have JI minus IJ, I have to put a negative sign and change the order of the terms. So I get negative E times epsilon IJK VI del cross AK. Well, one more step. This is negative E del phi j. Now, because B is del cross phi, I'm going to use that. Minus E del AJ by del T. And I'll also absorb the minus sign by shifting I and J. If I interchange I and J, because of the antisymmetry in the epsilon tensor, I will get another minus sign, which will cancel the minus sign here. So plus E times epsilon JIK VI BK. Right? There's a very specific reason I'm doing this, because it's easier to identify this as V cross B, because the jth component of V cross B is epsilon JIK VI BK. So it turns out very nicely. So that gives me negative, I'll write all this again, E times del phi. Well, let me write it like this. Plus E times del A by del T, the jth component of that. So that you can clearly see I'm getting the electric field there. And then here I have E times V cross B, jth component thereof. So I'm getting negative, well, the electric field has got a negative sign. So I'm getting the electric field E times the electric field E plus E times V cross B, the jth component thereof. So the jth component of the generalized force is precisely what you know and love to be the Lorentz force. So we have identified, so we'll write here. Therefore, F Lorentz is precisely E times, this is something that you've learned from University Physics 2 onwards. So that should be compared with this. So we conclude that Qj is just the jth component of the Lorentz force. So now we have enough confidence in this process that we can now form a Lagrangian. So that's our next step. The Lagrangian, the equations of motion are right there, but now let's write the Lagrangian that would have given us that very equation. So to form the Lagrangian, what we have to do is we've got to imagine, first we're going to do everything non-relativistic, then we're going to do relativistic. So we're going to imagine a particle of mass m, charge E, moving. When I say E, I don't necessarily mean electric charge of the electron. I just mean some generic charge. I could have called it charge little q, but that would confuse you with the generalized coordinates qi. That's why I want to keep it as E. So you're moving in a generic E and a B field. Okay, so we are going to do the non-relativistic case first, and then we'll do the relativistic case. Non-relativistic means it's not moving fast compared to the speed of light. So v much less than the speed of light c. The Lagrangian is going to have a kinetic energy term because it's a single particle. It's just 1/2 mv squared minus the potential energy function, which is your generalized potential, that. So let me write it down. L is going to be 1/2 mv squared minus E phi plus E times V dot A, which is VI AI. All right, so we can certainly, that's a Lagrangian, and we can, our next aim is to form the Hamiltonian, the Jacobi integral, and so on. The equations of motion are going to be precisely, F equals ma, where F is that. So that part is easy. So I'll just do this one. The canonical momentum. What's the canonical momentum? Well, the canonical momentum is going to be pi, which is del L over del qi dot. Well, qi dot is vi in our language. So del by del vi of the entire Lagrangian. So let me copy that down. This 1/2 mv squared, I'm going to write as 1/2 mvi vi, because v squared is vi vi by the Einstein summation convention. E phi, and then here I have plus E times VI AI. Then it's very clear when I differentiate, I'm going to lose the 2 factor here. So that gives me MVI. This does not depend on VI, so that term won't contribute. And then I just have a contribution coming from here, plus E times AI. So that's our amazing result. The true momentum in electromagnetic theory is not just mv, but also has got E times A. For those who have studied electromagnetic theory, this will come again as no surprise. So this is our electromagnetic momentum. Now we are so close to doing the Hamiltonian, we should probably do that next. So let's form the Hamiltonian. To form the Hamiltonian, you have to do the Legendre transformation, which gives us the velocity in terms of the momentum. Well, that is rather easily done in this particular case. So let me do that next. I just have to solve for V in terms of P. Well, that's easy. Therefore, VI, I'll use this one. VI is equal to PI minus E times AI divided by M. Or if you wanted to write it in the vector form, you can write it in the vector form also. V equals P minus EA over M. So that's our Legendre transformation. To write the Hamiltonian, we have to form the following quantity. P dot V minus L is a Hamiltonian with P given by, with V given by this. So let's go ahead and do this. So that's, I'll stick with the vectors because it's kind of fun to do vectors. EA over M minus the Lagrangian written entirely in terms of the momentum and not in terms of velocity. So I have to write that here as 1/2 M. Instead of V squared, I'm going to write it as V dot V instead of V squared. So that's P minus EA over M dotted with P minus EA over M. And then because of the minus sign, this term becomes a plus sign and that term becomes a minus sign. And here again, you have to write, I'll go back to writing this as V dot A. So I'm going to write this as V dot A. So this becomes E of P minus EA over M dot A. So this is not very difficult. You'll notice that you're going to get many terms. So one of the M factors will cancel out here. So that's going to give you 4 terms. That's going to give you 2 terms. So let's actually look at all the terms that come. I get P dot P. Actually, you know what? When I look at this term and this term, they can be combined because I can write this as P minus EA times that. So here's a lucky break. So this is just P minus EA over M dot P minus EA over M if I combine this term and this term. And then I have negative half of those terms. Okay. Oh, actually, I only have P minus EA. I don't have divided by M. Excuse me. I just have P minus EA because that's P and that's EA. There's no M. The M comes only in this term. Minus 1/2. The first term doesn't have P minus EA either, M either. So that's P minus EA dot P minus EA over M. That's good. Plus E phi. So I have a whole quantity minus half of that quantity. So that so I end up getting half of it. So P minus EA. When you dot something, same thing twice, it's the same thing squared, divided by 2M plus E phi. So that's our Hamiltonian. We'll save this for now because this Hamiltonian will be compared against what we will call the Jacobi integral very soon. So that's a important step in our understanding of the electromagnetic Lagrangian and Hamiltonian. Now, what is the object known as the Jacobi integral? So this part may be new to many of you. The Jacobi integral is a very specific integral. It's like the Hamiltonian, but it's not quite the Hamiltonian. It's actually more general than the Hamiltonian in a sense, because to write the Jacobi integral, you don't need to perform the Legendre transformation. There are some specific situations in which the Legendre transformation could be singular. So this keeps you from ever having to hit that singularity. So in a sense, it's more general. But for most cases, it'll be the same. I'll save the Hamiltonian here so you can see it when we do the Jacobi integral and compare it with that. It'll turn out to be almost the same. So what is the Jacobi integral? Here's some theory first. Obviously, it's named after Jacobi, who first found it. So he took a Lagrangian that's very general. It depends on Qi, it depends on Qi dot, and it depends on time. And he asked himself, under what conditions is something conserved? So to do that, conserved means the time derivative is equal to 0. So let's try to find the time derivative, the total derivative of the Lagrangian. Total derivative is first of all equal to the partial derivative with respect to time plus the partial with respect to Qi times Qi with respect to time, and that's Qi dot. Then the partial with respect to Qi dot, and the derivative of Qi dot with respect to time, which is Qi double dot, also known as the acceleration. Okay, now let us use the equation called the Euler-Lagrange equation. The Euler-Lagrange equation is the following: d by dt of del L by del Qi dot is equal to del L by del Qi plus only terms that don't involve, because Lagrangian already takes all the conservative terms. The Lagrangian is T minus U, where U is a conservative potential energy. So Q here has only got terms that are not conservative. So I call it Q prime, but prime is not to be confused for derivatives. Prime is a designation that means that we only take into account dissipation terms only. Because whatever part of the generalized force that's not dissipation and has got a potential energy function has been absorbed into the U function in the Lagrangian, because L is equal to T minus U. All right, with that understanding, let me substitute here for, what I'll do is I'll substitute for the del L by del Qi over there. Okay, so we're trying to find a conserved quantity. So let us try to see what will happen if this is a completely different step. I want to show you that we'll lose a bunch of terms. Let's try to see what happens when we do this total derivative. If I do this total derivative, my first term will be d by dt del L by del Qi dot times Qi dot. And the second term is going to be plus del L by del Qi dot times Qi double dot. So I'll just by using the product rule of Leibniz. So this term I have over there, the Qi double dot term. So what I'm going to do is, instead of the Qi double dot term, I'm going to substitute these things here. So del L over del Qi dot times Qi double dot is simply equal to d by dt del L by del Qi dot times Qi dot minus this thing here. But instead of writing d by dt del L by del Qi dot, I'm going to write the right-hand side. Okay, so that gives me del L over del Qi plus Qi prime times Qi dot, because that Qi dot is still there. So I have written this acceleration term as two terms like that. So I'm going to replace the acceleration term there with these terms. So now I'm going back to the original equation, which I'll call star. Put this in star. I'll call this, I'll call dagger. Put dagger in star. Then I have dl by dt equals del L by del t plus del L by del Qi dot. And now I'm putting, for this acceleration term, these two terms. So I get plus d by dt del L by del Qi dot minus, I'm going to parse this out. So that gives me del L by del Qi qi dot minus qi prime times qi dot. Observe, lo and behold, we have a cancellation. These two terms are exactly equal. So now, Jacobi at this point paused and said, what if we don't have any dissipation? No air resistance, nothing. So no dissipation. So this term will be 0. Also, we'll assume the Lagrangian does not depend explicitly on time. So no explicit time dependence. So that term will also go to 0. Then you just have dl by dt equals d by dt of stuff, which means d by dt of L minus that, or that minus L, must be equal to 0. So that's the important thing that Jacobi found. We'll write there. Therefore, d by dt of del L by del qi dot minus L is equal to 0. And if d by dt of something is equal to 0, that something must be a constant. That constant is called a Jacobi integral J. So it's del L by del qi dot minus L equals constant. You might think, how is the Jacobi integral any different than a Hamiltonian? It's not terribly different than a Hamiltonian, because if you think about it, del L by del qi dot are precisely the canonical momentum pi can I. And so the canonical momentum times qi dot minus L is precisely how you form the Hamiltonian, except you don't bother writing qi in terms of the canonical momentum. So that's the only difference. It is like a halfway step it's like forming the Hamiltonian without bothering to write everything in terms of the canonical momentum. That's for the Jacobi integral, if you want to think about it like that. So let's find the Jacobi integral for this problem, because it's one of the things I've asked you to do initially. So one of our goals is to write the Jacobi integral. All right, so let's do that. So what does Jack look like for this step? So the JEM, well, del L by del qi dot. I believe I've already got that. It's here. So that's just MVI plus EAI. That times qi dot, which is another VI, minus the Lagrangian, which is 1/2 mv squared, just right here. Because of the minus sign, I get plus E phi minus E VI AI. Observe that the E AI VI term cancels out. So the Jacobi integral for electromagnetism is just 1/2 mv squared plus E phi. And that is equal to a constant. This is the origin of the old saying that magnetic forces do not do any work, because what is constant is the total kinetic energy plus the electrostatic potential energy. Okay, so we'll write here, magnetic forces do not do any work. And because they don't do any work, by the work energy theorem, they don't contribute to the total energy of the system. All right, the last part of this video is to repeat this for the Hamiltonian and the Lagrangian in the relativistic framework. So If you've studied relativistic classical mechanics, then you all know that you have a great thing that Einstein said, which is E equals mc squared. And so that is going to be our starting point for the relativistic treatment. So Einstein's equation must be used. So the what we can do is we can write the Hamiltonian first, because the Hamiltonian will just be the total energy, and it's going to be P dot V minus the Lagrangian. So this is one way of finding the Lagrangian, is to find the Hamiltonian first. Because Einstein said E equals mc squared, in a sense, we know the Hamiltonian before we know the Lagrangian. So this is a very interesting situation where the Lagrangian is the more mysterious object than the Hamiltonian. So P here is m times V, where m is this dilation factor gamma times m naught. M naught is known as the rest mass. And the relativistic dilation factor gamma is 1 over the square root of 1 minus v squared upon c squared, where c is the speed of light in vacuum. I believe it's 3 times 10 to the 8 meters per second. So that's going to be your basic setup. Now, let's write down this equation. So I'm going to get the left side is E, which is mc squared. So I'm going to get mc squared equals m squared v squared, because I have v dot v, which is v squared, minus the Lagrangian L as a function of r and v. So we have, in this way, found the Lagrangian. The Lagrangian L as a function of r and v is just m times v squared minus c squared. Yeah, it's v squared minus c squared. Now observe that v is always less than c, since nothing can travel faster than light. So here we're going to have a negative sign, because I can pull out this and write it as c squared minus v squared. So this is going to be negative m naught. I'm going to write m as m naught times the gamma factor times c squared minus v squared. Okay, all I've done here is taken the negative sign outside, interchange the order of c and v, c squared and v squared, and written m as m naught times gamma using the rest mass. Now gamma is 1 over that. So what I can do here is write that down. 1 over the square root of 1 minus v squared over c squared. And here I'll take the c squared outside. So I get c squared times 1 minus v squared over c squared. So that's a really interesting situation. I have the a square root survives when I cancel out. So this gives me negative m naught c squared times the square root of 1 minus v squared by c squared. And now I can go ahead and take one of the c factors inside. When I take a single c factor inside, it becomes c squared, and it gets rid of the c squared down there. And then I'm only left with a single c up here. So m naught c root c squared minus v squared. That is a relativistic Lagrangian. Einstein certainly didn't bother saying that. It's less catchy than E equals mc squared. You will agree with that. It's certainly less catchy than E equals mc squared. So now that we have the relativistic Lagrangian, it's, by the way, a good idea to check if this is indeed true. So one way to check is to find the canonical momentum. So let's do that quickly. The canonical momentum is simply going to be mv because we are not introduced any electric and magnetic fields yet. So let's check what it's going to be. P is going to be equal to del L over del V. And when I differentiate this, V is inside here. So when I differentiate it, I have to use the chain rule. So it's going to be m naught C. And then I differentiate the inside function. So that's going to be negative 2V. And then when I differentiate the square root, I get a negative sign again. So I get negative 2 square root of C squared minus V squared. So that negative sign gets taken care of. The 2 gets taken care of. And I have m naught. I can take the C inside the square root sign by dividing the denominator by C squared. So that gives me m naught times, that's a V vector there, V divided by the square root of 1 minus V squared over C squared. And that precisely is m naught times gamma, which is mv. So this recovers for us the canonical momentum. Okay. Now, by the way, the Hamiltonian, written in terms of all the, in terms of Einstein's formula, because H is equal to E. So I can write the Hamiltonian now. It's just mc squared. Now m, this can be written as p squared c squared plus m naught squared c to the 4. I believe physics students are fond of writing a right angle triangle to remember this rule. Okay, so you have mc squared on this hypotenuse, and then pc on this side, and m naught c squared on this side. So it's like a Pythagorean theorem for relativity. Now our next step is to go and form the relativistic Lagrangian, incorporating the electric and magnetic fields in the process. So what we'll do in order to form the relativistic Lagrangian is we'll take this relativistic Lagrangian for a particle simply moving in space. That's really what this is, but now suddenly encounters an electromagnetic field. So all we have to do is, instead of writing 1/2 mv squared for the kinetic energy term, we have to write this, and we'll keep the rest the same. So the relativistic Lagrangian will simply be the following. L rel, which is a function of R and V, is going to be negative m naught C, copying that, root C squared minus V squared, and then I'm copying this, minus E phi, I'll write this as the dot product, plus E times V dot A. So that's going to be our relativistic Lagrangian. Let us try to find the equations of motion, because we are going to show that Lorentz force is a relativistic force. Okay, that gives us the proof of that statement. So now we are going to apply the Euler-Lagrange equations. All the constraints, there are no constraints in this problem. It's just a particle flying around in an EM field doing whatever it does. So it's just going to be the usual Euler-Lagrange equation, d by dt, del L over del qi dot, which is xi dot or vi, minus del L over del qi, which is just going to be xi. I'll write it as the ith component of r, or I, equal to 0. So what does that give us? D by dt, let's first differentiate the Lagrangian with respect to v. This step I've already done while finding the canonical momentum there. So I can write this as del L by del V can be written as mv. So I'll write it as m naught gamma vi, because it's the ith component. Oops, that's not the only term with a velocity though. You also have velocity coming from this term. So when I differentiate that, I'm going to get plus. So I'm differentiating with respect to velocity here. So I'm going to get E times with respect to VI. So I'm going to get AI. And then negative del L by del Ri. The Ri terms are only in the potential, in the scalar potential and the vector potential. Because of the negative sign here, I'll get a negative of a negative or plus E times the ith component of the gradient of phi. And then that becomes a minus, minus E times Vj times del Aj over del Xi. All that equals 0. So I have, this is just the canonical momentum. So that's d by, this is just an ordinary momentum P, which is mv. So this is pi. And then I have this term. So this gives me plus d by dt of EAI. Well, that's just E times del AI by del xj and del xj by del t, or dxj by dt, by using what's called the chain rule of partial derivatives. Okay, so instead of writing it as dAI by dt, I wrote it like that. And then the remaining terms you still have. So I'll write that here, E times del I phi minus E times Vj del Aj by del Xi equals 0. So now you must be sensing there's something very interesting happening, because this term is just Vj. And so you have del Ai over del Xj minus del Aj over del Xi. It's the curl term that gives you the magnetic field. So we are getting very warm indeed. So let's go to the next step. So that gives me a dpi by dt. I'll bring everything to the right side. So that's equal to negative E, the ith component of the gradient, del I phi. And then this I'll write as plus E times, I brought this to the other side. So that becomes positive, that becomes negative when I bring it to the other side. So that's del I Aj minus del J Ai Vj. And by the exact same process that we did before, we can identify this as the gradient of the magnetic field. And so this gives me, this is just E times electric field plus E times V cross B. So I have recovered the Lorentz force. F lor is equal to that. We have proved by doing this that the Lorentz force is relativistic in origin. This is why Lorentz got the Nobel Prize for writing this. He didn't simply combine E times E with E times V cross B. Any child could have done that, but he actually showed that you get the relativistic Lorentz force from this Lagrangian, okay? And that's Lorentz's great achievement, which got him the Nobel Prize. So Lorentz force is relativistic. What is the Hamiltonian? Well, the Hamiltonian simply comes from replacing P with the proper canonical momentum. Well, the canonical momentum that we have is this, all right? So all we have to do is write it as, instead of MV, we write as P minus EA, okay, over there. And so the Hamiltonian H is the square root of P minus EA squared C squared plus M naught squared C to the 4. And then you have to also have the electric potential term, E phi. And I will leave it an exercise for the interested students to show the Hamiltonian equations of motion. Well, one of them will recover the so-called Legendre transformation, and the other one will give the Lorentz force. Okay, so Pi dot is negative del H over del Ri. That'll give you the Lorentz force, and then Ri dot equals del H over del Pi. That'll recover for you the Legendre transformation. So that's so I'll write here. This is the Lorentz force. And that's the Legendre transformation. So in this way, we have done all the parts, or at least sketched all the parts of the problem. We've written the relativistic Lagrangian and Hamiltonian. We've shown the Lorentz force is relativistic in origin using the Lagrangian approach, and Hamiltonian approach, I'm leaving it as an exercise for the interested student to show the same thing. Okay.